Welcome to The Explainer, where we take complex source material and turn it into clear, actionable insights. Today, we're uncovering a fascinating physical phenomenon that often hides right in plain sight within massive industrial engineering projects. It's an unseen force, driven by the simplest of elements that can literally tear heavy steel apart. Let's get right into it.
Okay, I want to kick things off with a scenario that honestly sounds almost unbelievable. I want you to imagine a massive, heavy, industrial steel pipe stretching out, say, 30 meters. How on earth could a completely normal, simple rainstorm cause the ends of that thick steel pipe to physically lift and bend 18 centimeters into the air?
18 centimeters. I mean, that is a massive structural shift. When physical forces of this sheer scale just suddenly manifest in a rigid system, they inevitably lead to catastrophic industrial failures. So what exactly is this hidden force? And why does it manage to catch even the most seasoned engineers completely off guard?
Let's look at Section 1, the thermal bowing phenomenon. The answer to our mystery lies in something called thermal bowing. Basically, thermal bowing is differential expansion. It's caused when there's a significant temperature discrepancy between the top and the bottom of a horizontal pipe. Picture a pipe that's only partially filled with a really cold liquid on the bottom, while the hot sun beats down on the empty top half. Or imagine a sudden downpour of freezing rain hitting the top of an intensely hot pipe. The hot side expands much more rapidly than the cool side, and because they're physically attached to each other, well, the pipe has absolutely no choice but to warp and bend to accommodate that difference. It's wild to think about.
This brings us to Section 2, uniform expansion versus gradients.
To really grasp this, let's think about a uniformly heated pipe that is completely free to move. As it gets hot, it just lengthens, right? It elongates without any internal stress whatsoever. But what if that exact same pipe is locked in place? Say it's axially constrained at both ends. It can't lengthen anymore. Instead, it builds up massive internal compression. And if it gets hot enough, that compression causes the metal to yield or even buckle laterally.
But thermal bowing introduces a completely different dynamic into the mix. Uniform thermal expansion, as we just talked about, causes internal stress and pure compression if the pipe is trapped. A thermal gradient, however, where one side is distinctly hotter than the other, actually forces the pipe to curve. And because it's curving, it generates tensile forces at the ends. It literally pulls on its constraints rather than pushing against them. It's a total game changer. Now, in the real world, things are rarely that neatly separated. So let's move to Section 3, the overlap of thermal effects. What's really fascinating here is mapping out exactly what happens when uniform expansion and thermal gradients happen at the exact same time. The pipe is trying to expand uniformly, pushing outward in compression, but that temperature difference is making it bow, which creates pulling, tensile forces. The result is what engineers call an effective deformation. The compression from the uniform heat and the tension from the gradient essentially fight a massive, complex tug-of-war right there inside the solid metal. This dynamic builds into these pre-buckling and post-buckling phases. And here is the crazy part. Paradoxically, the pulling tension from a thermal gradient can actually delay the structural buckling caused by uniform expansion. But it is a serious double-edged sword. While it might prevent immediate compression buckling, the gradient can iteratively stack tensile stresses in the pipe to incredibly dangerous levels as temperatures fluctuate over time. Engineers simplify this incredibly complex interaction using a dimensionless number called the zeta value. And the crucial takeaway is this. If the zeta value is greater than 1, uniform expansion and compression win out. If it equals exactly 1, well, the forces beautifully cancel each other out into deformation with almost zero stress. But if zeta drops below 1, the thermal gradient dominates, and that turns the entire pipe system into a highly stressed, tension-loaded hazard just waiting to snap. To see just how destructive a zeta value of less than 1 can be, let's explore Section 4, an industrial engineering mystery. Tracing the timeline of this specific facility reveals a totally baffling pattern. Back in the 1970s, an ammonia and fertilizer plant was built, and for a full decade it operated flawlessly, no issues. Then routine maintenance was performed to restore some insulation. Suddenly, the piping connections started cracking severely, like clockwork, every 4 months. They brought in international experts, ran complex computer models, and even replaced the support springs, which somehow made the cracking even worse. The system was theoretically perfectly safe, yet it just kept tearing itself apart.
And you have to remember, the stakes here were incredibly high. This system was transferring volatile hot gas at an extreme 34 bar pressure. The transition point in the pipe dropped dramatically from a carbon steel cold wall section sitting at 200 degrees Fahrenheit straight into an alloy steel hot wall section burning at 1500 degrees Fahrenheit. The solution was finally uncovered by a sharp-eyed engineer who just started comparing before and after maintenance photos. During that routine maintenance 10 years in, the contractors had missed a tiny, seemingly insignificant strip of external insulation right over a critical weld. In the original design, the exposed weld hovered safely at about 500 degrees. But because of this one tiny missing chamfer of insulation, that exposed joint was now rocketing to a blistering 1500 degrees Fahrenheit. But you might be wondering, why did it only crack every 4 months? Well, the answer, incredible to say, lies in the rain. Whenever a sudden rainstorm hit the plant, the cool water splashed right onto that tiny, uninsulated 1500-degree weld. In seconds, the top of the pipe cooled drastically, while the bottom remained blistering hot. This instantaneous thermal gradient induced thermal bowing so violent it generated an unbearable 720 megapascals of stress. That is way beyond the yielding limit of the steel, and so it snapped the weld again and again and again. A tiny strip of insulation and a simple rainstorm nearly destroyed a massive facility. So how do we stop this from happening? Let's look at Section 5, Preventing Pipe System Failures. While the math we looked at earlier is undoubtedly complex, modern engineering tools make predicting this surprisingly simple. In standard stress analysis software like Caesar-I, there is literally a single field in the special execution parameters called thermal bowing delta temperature. Engineers can simply plug in the estimated temperature difference between the top and bottom of the horizontal pipe, and the software automatically calculates those massive tensile forces we've been discussing. The source material leaves us with a really clear checklist for best practices here. First off, actively identify vulnerable pipes. We're talking about anything outside exposed to the weather, or pipes carrying mixed phases of gas and liquid. Second, use rigid hold-down supports to physically restrain that bowing effect. Third, design the system with enough flexibility to handle the curvature if it does actually happen. You also want to pay special attention to sudden thermal drops near delicate welds or flanges. And finally, as a general rule of thumb, always run a test simulation assuming a 50 degrees Celsius temperature differential for any exposed pipe operating over 200 degrees. We walk past heavy industrial pipes, sprawling refineries, and massive structural beams every day, usually assuming their sheer size makes them invincible to something as simple as the weather. But as we've seen today, the simple collision of hot steel and cold rain can unleash physics powerful enough to tear solid metal apart. It really makes you wonder, what other invisible forces are silently stressing the infrastructure all around us right now? Keep questioning, keep learning, and thank you so much for joining me on this deep dive into the source material.